While the world fixates on 3IATLAS, the distant, mysterious interstellar wanderer gliding through the outer solar system, there's an even more pressing threat that many overlook. The year 2029 is etched in the sky, with an event that could change everything on the horizon. On April 13, 2029, an asteroid named Apophis, a true harbinger of chaos, will pass incredibly close to Earth, closer than any object of its size in recorded history. This colossal space rock, roughly 340 meters in diameter, will zip past at a distance of just 30,000 kilometers from the planet's surface. To put that into perspective, the orbit of our communication and weather satellites, like GPS, resides in the geostationary belt at a distance roughly 35,000 kilometers away. The International Space Station, by contrast, orbits at a much higher altitude, around 400 kilometers. On that day, Apophis, also known as the God of Chaos, will make an unprecedented pass through Earth's orbit. This asteroid is capable of unleashing the energy of hundreds of nuclear bombs if it collided with Earth. Yet the most frightening part is its near miss. The mass media and scientists have reassured the public that there is no immediate threat. However, beneath this confident narrative lies a much deeper uncertainty. The asteroid's trajectory and the forces acting upon it during this flyby are far from fully understood. The force of Earth's gravity, coupled with tidal effects, could alter Apophis's path, subtly changing its orbit for decades. Small shifts that occur in space are hard to predict, but the longer the timescale, the more they can magnify. There's a real chance that the 2029 encounter may not be a one-time event. It could be a catalyst for changes that make future encounters with the asteroid more dangerous. Let's break down the significance of this event. If the asteroid's trajectory were altered even slightly, it could have cascading effects on its orbit, potentially leading to a much more dangerous encounter years down the line. This is where the real concern lies. What if we're not truly as safe as we think? The official stance from NASA and the European Space Agency is reassuring. According to their current models, Apophis poses no risk of impact for at least the next century. They claim that their calculations are sound, and there's no need for alarm. Yet, beneath the calm, a quiet uncertainty lingers. Researchers, particularly those specializing in orbital dynamics, continue to scrutinize the asteroid's orbit, wondering about the unknowns that could lead to unexpected changes. While the flyby may appear harmless, it could set off a chain reaction. Imagine this. What if Earth's gravitational forces during the close pass shift Apophis's internal structure, disturb its surface, or alter its spin rate? These minute alterations could affect its trajectory in ways we can't currently predict. And what if the asteroid emerges from the flyby not quite as it was before? Its orbit adjusted ever so slightly, its path redirected in a subtle, almost imperceptible way. Such changes, though small at first, could accumulate over time, resulting in a much more unpredictable future. At present, Apophis follows a well-established orbit, tracked by radar and pinpointed against the backdrop of distant stars. But these models are based on a number of assumptions. Scientists assume a certain mass, a predictable spin rate, and a consistent surface composition. They assume that no unexpected forces will act on it. But what if the 2029 flyby introduces variables that we haven't accounted for? What if some of those assumptions are wrong? This is where the uncertainty lies. The changes triggered by the flyby might be so subtle that we don't immediately recognize them. The adjustments could take years to detect, and by that point, we may no longer be able to predict Apophis's future movements with the same confidence. The models that seem to guarantee safety may quickly become obsolete as new data emerges, forcing us to recalibrate our assumptions and forecasts. This scenario may sound like science fiction, but it is grounded in hard science. There are researchers in the field of planetary defense who are actively working on understanding these uncertainties. They are studying tidal forces, orbital shifts, and the tiny accelerations that could make a seemingly harmless flyby a much larger problem. The truth is, we just don't know what will happen after April 2029. The asteroid could stay on its predicted path, or it could experience a subtle but significant change that alters everything. The models we currently rely on give us a sense of security, but they also carry built-in uncertainties. As scientists refine their predictions, they are forced to confront the possibility that Apophis might not follow the trajectory we expect. While the most likely outcome may be benign, it's the tail scenarios, the low probability events, that could have devastating consequences. What happens if Apophis's orbit is shifted just enough to bring it back for another close encounter, or worse, a collision? This is why the research into Apophis continues. The data we gather in the coming years will be crucial in determining whether our safety projections hold or if the risk is much higher than anticipated. Until then, we are living on the edge of uncertainty, waiting for the next data points to either confirm our safety or send us back to the drawing board. The flyby of Apophis in 2029 will not just be an event to mark on the calendar. It will be a turning point, a moment in time when the theories we have developed could either be validated or challenged. Right now, we are watching and waiting, hoping that our models are correct. But what if in the wake of this event, our understanding of the asteroid changes fundamentally?
What if we realize, only after the flyby, that the assumptions we've based our safety predictions on are flawed? Let me explain why this matters. The existing models used by NASA, the European Space Agency, and other agencies to assess the risk of Apophis are based on a number of key assumptions. For instance, scientists have built these models assuming that Apophis's mass is known, that it rotates at a specific rate, and that its surface composition is uniform. They've based their predictions on these factors, and the results are comforting. Apophis is not expected to impact Earth anytime soon, at least according to the data we have right now. But there are gaps in our understanding. What if Apophis's surface is different from what we expect? What if its mass is greater than anticipated, or its rotation rate changes after the 2019 flyby? The problem is, we just don't know, and that uncertainty is what makes this flyby so critical. When Apophis passes close to Earth, the tidal forces from our planet's gravity will affect its structure. In a solid asteroid, this might not be a significant concern. However, if Apophis is a rubble pile, a loosely bound collection of smaller rocks and dust, those tidal forces could trigger surface shifts or landslides. We've seen similar events with other asteroids. When the surface material shifts, it could expose fresh rock, which has different thermal properties. This could alter the asteroid's temperature and, consequently, its thermal emissions, which would affect how we model its future trajectory. The key thing to remember is that even small changes in Apophis's surface, rotation, or mass could have profound effects on its orbit. A tiny shift, measured in millimeters per second, could slowly add up over the years, gradually altering its trajectory. And while it might take decades to see the full impact of these changes, by then it could be too late to adjust our predictions. The flyby of 2019 could mark the moment when these subtle, almost imperceptible changes begin to compound, shifting Apophis's path in ways that we haven't accounted for. This is why scientists continue to study Apophis so intensely. They know that after the flyby, we may need to reevaluate everything. The models we rely on today might be completely out of date, and new risks could emerge. The flyby is not just a close encounter. It's a test of our models, our understanding of asteroid dynamics, and our ability to predict the future. It's also worth noting that this is not just about Apophis. It's about the broader issue of planetary defense. The 2019 flyby represents a key moment in our ability to track and predict the behavior of asteroids. If Apophis changes its orbit in ways we didn't anticipate, It could open up a whole new area of research and risk assessment. The more we learn about Apophis, the more we'll understand about the potential threats we face in the future.
And that knowledge is crucial if we want to protect our planet from the dangers posed by asteroids. At the moment, the majority of the research into Apophis is focused on refining the models. But the real breakthrough will come when we get the data we need to either confirm or challenge our current understanding. Until then, the asteroid's future trajectory remains uncertain. We're doing everything we can to prepare, but the unknowns are what keep experts up at night. What if we miss something? What if the flyby of 2029 changes everything? The answers to these questions could reshape our entire approach to planetary defense. Now, I know that all of this might sound a little unnerving, but the truth is, this is how science works. It's about asking questions, refining models, and constantly reassessing what we know. It's about recognizing that we can never be completely certain about anything, but that doesn't mean we should stop trying to understand the world around us. This is exactly why we need to keep watching Apophis closely. The more we learn, the better equipped we'll be to handle whatever comes our way. In the coming years, as the 2029 flyby approaches, planetary defense experts will be watching Apophis with bated breath. While we may feel safer now, there are critical gaps in our knowledge that need to be addressed before the encounter. Every detail matters, every measurement, every assumption that needs to be confirmed. Without precise data on Apophis's mass, rotation, surface composition, and other key parameters, our predictions of its future trajectory will be incomplete at best and dangerously flawed at worst. This is why some scientists are so focused on gathering additional information, even when the public narrative assures us there's no immediate threat. There are still so many unanswered questions. What if, after the flyby, we find out that Apophis's mass is slightly different than we thought, or that its surface is much rougher than expected? What if its rotation rate changes in ways we couldn't predict? Each of these factors, though seemingly minor on their own, could have a huge impact on how the asteroid interacts in the years to come. For example, imagine if Apophis's rotation rate speeds up during the flyby, caused by tidal forces from Earth's gravity. This would affect the asteroid's thermal properties and alter its thermal emissions. The Yarkovsky effect, which describes the way an asteroid is pushed by the radiation it emits, would become more pronounced. Even small changes in the surface, such as the exposure of fresh rock, could dramatically affect how the asteroid interacts with solar radiation. This, in turn, would impact the asteroid's orbit. We can't afford to overlook any of these possibilities. The goal isn't just to observe Apophis and hope for the best. It's to gather the data that will allow us to refine our models, narrow down the uncertainties, and develop contingency plans for every possible outcome.
As we get closer to the flyby, the importance of these measurements will only increase. This isn't about being alarmist. It's about being prepared, making sure we understand as much as we can about Apophis before it makes its approach. Another factor that complicates things is the asteroid's potential to affect the technology we rely on every day. Apophis's flyby will occur close to Earth's satellite infrastructure, so close that it may disrupt satellite orbits. While the asteroid itself is unlikely to collide with any satellites, the gravitational forces it exerts could be enough to nudge some of them out of place. This could trigger a cascade of collisions, especially in geostationary orbit, where thousands of satellites are positioned. If one satellite is nudged, it could collide with another, creating debris that poses a serious hazard to other spacecraft. And yet, this is just one aspect of the potential fallout from the flyby. In addition to the risk of satellite damage, there's the threat of the asteroid affecting the very systems that allow us to track it in the first place. Space weather, which is heavily influenced by solar flares and coronal mass ejections, poses a direct risk to the instruments we use to monitor asteroids like Apophis. The timing of these solar events could potentially coincide with the 2019 flyby, disrupting our ability to track the asteroid with the precision we need. Solar storms can degrade radar performance, interfere with satellite communications, and disrupt the sensors on spacecraft. If, in the midst of the flyby, a major solar flare or coronal mass ejection occurs, it could make it impossible to gather the data we need to accurately predict Apophis's future trajectory. This would leave us in a vulnerable position, forced to rely on incomplete or inaccurate data and struggling to manage an evolving risk. Even if everything else goes according to plan, space weather could throw a wrench into our carefully laid out monitoring strategies. The key takeaway here is that planetary defense isn't just about tracking asteroids, it's about managing a whole system of technological infrastructure that depends on precise measurements and coordinated communication. If the systems we rely on fail, or if unexpected space weather events disrupt our ability to monitor the situation, the consequences could be dire. While the asteroid itself poses a clear and present risk, it's the failure of our ability to track and understand it that may prove to be the greatest danger. There's also the issue of public communication. As the 2029 flyby approaches, space agencies like NASA and the European Space Agency will be under pressure to reassure the public that everything is under control. But the reality is much more complex. While official statements may downplay the risk, researchers behind the scenes will continue to study the asteroid, refine their models, and explore every potential scenario.
These efforts are crucial in ensuring that, should something unexpected happen, we are ready to respond. This discrepancy between public communication and the work being done behind the scenes is something that often goes unnoticed. On the one hand, agencies must provide reassurances to avoid panic, while on the other hand, they are fully aware of the uncertainties that exist. The scientific community is committed to exploring every angle, testing every assumption, and addressing every question that arises in the wake of new data. But no matter how much we prepare, the reality is that the final outcome is still uncertain. The 2029 flyby of Apophis is a defining moment in planetary defense, a moment that will either validate our current understanding of asteroid dynamics or force us to rethink everything we thought we knew. The data we collect in the coming years will be critical in shaping the future of planetary defense. And while the models may be reassuring for now, we must remain vigilant and open to the possibility that our predictions could be proven wrong. Only time will tell if we are truly safe or if, in the face of new information, we will find ourselves facing a much larger challenge than anticipated. As we approach the flyby of Apophis in 2029, it's important to acknowledge that this isn't just a one-time event. It's part of an ongoing, larger conversation about humanity's ability to predict and respond to potential asteroid threats. The flyby will undoubtedly provide valuable data, but it will also be the starting point for further research and analysis. The future of planetary defense will depend not just on what we observe on April 13, 2029, but on how we interpret and adapt that information in the years that follow. One of the most significant challenges in understanding Apophis and other near-Earth objects is the inherent uncertainty in our measurements. Every observation, every model, and every assumption carries some degree of error. As we've seen in the history of space exploration, new data can radically shift our understanding of asteroids. Take, for example, the observations of asteroids like Bennu and Ryugu. Initial models predicted solid, monolithic structures, but close-up imagery revealed complex, rubble pile compositions. These surprises force scientists to revise their models and rethink what we know about asteroid behavior. It's crucial to recognize that Apophis might not be as predictable as we assume. The data we collect during the flyby will be pivotal, but it may also reveal that we're missing key pieces of the puzzle. For instance, scientists are particularly concerned about the composition and internal structure of Apophis. If it's indeed a rubble pile, with its surface and internal components loosely bound together, the tidal forces from Earth's gravity could have a much more significant impact
than if the asteroid were solid.
These tidal forces could trigger small-scale movements on the asteroid's surface, shifting material, causing landslides, and even altering its thermal properties. What seems like a minor shift in surface material could have far-reaching consequences for Apophis's long-term trajectory. The Yarkovsky effect, the subtle force caused by the asteroid's rotation and its emission of thermal radiation, relies on the assumption that the surface remains relatively stable. If this assumption is wrong, our understanding of how Apophis will behave in the future could be thrown into disarray. In addition to the physical changes that might occur during the flyby, there's also the issue of the asteroid's spin. If Apophis is tumbling or rotating in an unpredictable manner, our ability to forecast its future movements becomes even more complicated. A tumbling asteroid doesn't have a predictable rotation pattern, which means it could be subject to erratic changes in how it absorbs and radiates heat. This, in turn, would affect the Yarkovsky effect and potentially alter its orbit in ways we can't currently predict. This adds another layer of complexity to the situation. While current models assume a steady spin, the reality could be much more chaotic. This is why precision is everything. The more accurate the data, the more confident we can be in our predictions. But as we continue to refine our models, we must remain cautious. The more precise our measurements become, the more we uncover the small uncertainties that could affect the outcome. If, after the flyby, we discover that Apophis's trajectory has shifted in ways we didn't anticipate, we could find ourselves in a situation where the risk assessment needs to be recalculated from scratch. And by then, it might be too late to act. Another important consideration is the possibility of multiple fragments breaking off from Apophis. While it's not a likely scenario, it's still one that scientists are carefully studying. If Apophis gains weight during the flyby, or if its structural integrity is compromised, it could fragment into smaller pieces. These fragments might follow different paths, which could lead to a situation where multiple impact sites emerge. This is one of the many what-if scenarios that researchers are trying to model. What happens if the asteroid fractures into pieces, and what impact would that have on Earth? In the face of all this uncertainty, the role of planetary defense is clear. It's not just about preventing a direct impact, but about understanding the full range of possibilities and being prepared for whatever might happen. We may be fortunate, and the flyby might pass without incident, but we must also be ready for the unexpected. The research and preparation that go into planetary defense are ongoing and multifaceted. They require collaboration between space agencies, researchers, and governments to ensure that we are as prepared as possible, no matter what the future holds.
The technology and tools available for monitoring asteroids have advanced dramatically in recent years. With the use of ground-based telescopes, radar systems, and spacecraft, we can track Apophis with remarkable precision. But even with these advancements, we are still limited by the available data. To truly understand the risks posed by Apophis, we need even more accurate measurements, particularly in the areas of its mass, rotation, and surface composition. This is why missions like OSIRIS-APEX and the proposed Ramses mission are so crucial. They will provide the kind of close-up data that we can't get from Earth-based observations alone. These missions will be our best chance to gather the information needed to make informed decisions about planetary defense. While the public may be reassured by statements from space agencies like NASA and ESA, it's essential to understand that these organizations are operating within a framework of uncertainty. When they say that Apophis poses no risk for the next century, what they really mean is that, based on the best available data, the probability of an impact is extremely low. But the key word here is probability. There is always a small chance, however remote, that something could go wrong. The goal of planetary defense is to account for those low-probability, high-consequence scenarios,
and ensure that we're prepared for whatever comes our way. Ultimately, the flyby of Apophis is a moment that will define our understanding of planetary defense. It's not just about this single asteroid. It's about the entire field of asteroid risk assessment and how we respond to the potential threats that lie beyond our immediate reach. The lessons we learn from this event will shape our strategies for decades to come. As we move closer to April 2029, the importance of continued research, careful observation, and rigorous modeling cannot be overstated. We're about to witness a critical test of our ability to understand and mitigate the risks posed by near-Earth objects, and the outcome could have far-reaching implications for the future of our planet. As we continue to examine the threat posed by Apophis and the potential outcomes of its flyby, it's crucial to keep in mind that planetary defense is a complex and evolving field. The mission to better understand Apophis isn't just about collecting data, it's about learning from every flyby, every close pass, and using that information to refine our models for future encounters. This is why the scientific community is so dedicated to ongoing research. It's a commitment to building a more resilient and prepared society in the face of astronomical threats. In many ways, the 2029 flyby is a rare opportunity. It's not every day that a massive asteroid passes so close to Earth. This encounter will give us a chance to test our current models and technologies. It will allow researchers to observe the effects of tidal forces on an asteroid of Apophis' size and composition.
These observations will inform not just our understanding of Apophis, but our general understanding of how near-Earth objects behave when they come in close proximity to our planet. This knowledge will be vital for managing future risks from other asteroids, many of which are still being discovered. But we also need to consider the broader implications of this flyby. What happens if, after the flyby, we realize that Apophis' orbit has been altered in ways that make future encounters more frequent or more dangerous? What if this flyby pushes the asteroid into a resonance with Earth, causing it to return at regular intervals? These are the long-term questions that scientists are already asking themselves as they prepare for the flyby. The reality is, while the initial danger of an impact may seem small, the long-term risks may be much harder to predict. It's not just about one flyby. It's about how that flyby could influence the trajectory of Apophis for centuries to come. One of the most important aspects of planetary defense is the ability to adapt. Even if we have the best models and the most accurate data, we must always be ready to adjust our understanding based on new information. This means that we cannot become complacent after 2019, assuming that everything will be fine. Instead, we need to stay vigilant and continue refining our models as new data comes in. This is how science works, by constantly evolving and refining our understanding based on the best available evidence. The flyby of Apophis could also shed light on the physical processes that govern the behavior of asteroids. As we've seen with other asteroid missions, like the OSIRIS-REx mission to Bennu, close-up observations often reveal unexpected findings. In Bennu's case, the surface turned out to be much looser and less compact than expected, suggesting that its material was far more fragile than anticipated. Similarly, we may find that Apophis' surface is not as solid as previously thought, which would have major implications for how we model its behavior. But even more surprising could be the internal composition of the asteroid. Asteroids like Apophis are often thought to be made of solid rock, but this isn't always the case. Some asteroids are made up of loose, fragmented materials held together by weak gravitational forces, what scientists refer to as rubble piles. These rubble pile asteroids behave very differently from solid ones, especially when subjected to tidal forces. Instead of staying intact, their surface material can shift, slide, and even collapse.
If Apophis is a rubble pile, the tidal forces from Earth's gravity could trigger significant changes in its structure, potentially altering its future trajectory in ways we haven't fully accounted for. As we refine our models, we also need to consider the broader risks associated with asteroids passing through Earth's orbital path.
While Apophis may not pose a direct threat during the 2029 flyby, future close encounters could pose more significant risks. As Apophis's orbit shifts due to tidal forces, we could see more frequent close passes in the years to come. The risk of a collision might not be immediate, but it could grow over time as the asteroid's path becomes less predictable. This is why planetary defense experts stress the importance of continual monitoring, long-term risk assessment, and preparation for future asteroid threats. One of the most significant challenges in planetary defense is the uncertainty of the long-term future. Asteroids are difficult to track, and their behavior is even harder to predict over long timescales. Even with the most advanced technology and the most accurate models, there are still many variables that remain unknown. For instance, we still don't fully understand how the Yarkovsky effect, the subtle push created by the asteroid's rotation and thermal emissions, will evolve over time. This effect is responsible for small but significant changes in an asteroid's orbit. If we don't fully understand how it works, we may miss subtle but important changes in Apophis's path. But this uncertainty is not a reason to panic. Instead, it's a reason to continue working and refining our models. It's a reason to keep gathering data and pushing the boundaries of our understanding. Because while we may not be able to predict every possible outcome, we can improve our chances of identifying and mitigating the risks in time. The scientific community is having hard at work to make sure that we are as prepared as possible for whatever comes next. And that work is vital, not just for Apophis, but for every asteroid that crosses our path. As we continue to study Apophis and prepare for the flyby, we must remember that this is just the beginning. The real work begins after the flyby, when we will need to reassess the data, update our models, and determine whether any changes to Apophis's trajectory could increase the risk of a future impact. It's not enough to simply track the asteroid. We must also be ready to act if something unexpected happens. In the end, planetary defense is about more than just avoiding a single impact. It's about understanding the full range of possibilities and preparing for every eventuality. As we approach April 2029, the world will be watching, but we must also be preparing for what comes after the flyby. This is not just about one asteroid. It's about the future of planetary defense and the survival of life on Earth. As we move closer to the 2029 flyby of Apophis, the importance of our preparation cannot be overstated. The advancements in space technology and asteroid monitoring over the last decades have significantly increased our understanding of near-Earth objects, but there is still much we don't know.
The 2029 flyby will be a test, not just for our models, but for the entire planetary defense infrastructure that has been developed to track, predict, and protect us from asteroid threats. However, as much as we've learned, there remains a crucial piece of the puzzle: the unknowns that only real-world data will reveal. The true challenge lies not in what we expect to happen during the flyby, but in how we adapt to what we didn't expect. Space exploration, like all scientific endeavors, is built on uncertainty. No matter how advanced our telescopes, radar systems, or spacecraft become, there will always be variables that escape our detection. And as history has shown, it's these very uncertainties that often shape the future of planetary defense. We only need to look at past asteroid encounters to realize that the smallest, most seemingly insignificant detail can drastically alter the trajectory of an asteroid. That's why the 2029 flyby isn't just a scientific event. It's a turning point in how we approach planetary defense in the future. One of the key uncertainties that researchers are working to understand is the way in which Apophis's orbit will change as it passes through Earth's gravitational field. While we've tracked Apophis's movement for decades, we can't predict with absolute certainty how the asteroid will respond to the tidal forces that will act on it during the flyby. If Apophis is a solid body, these forces may have a negligible effect. But if it's a rubble pile, an asteroid made up of loose, fragmented materials held together by weak gravity, the tidal forces could cause a dramatic shift in its structure. It could cause the asteroid to deform, its surface materials shifting and rearranging. This would in turn affect its future path, potentially making future close passes more frequent or even more dangerous. At present, we are operating under the assumption that Apophis's orbit will be predictable for the next century. This assumption is based on the data we have now, data that has been meticulously gathered over the years. However, as the 2029 flyby approaches, it's important to acknowledge that this data is not infallible. Even the most carefully calculated models are based on assumptions that may not hold true after the flyby. The close encounter with Earth may introduce variables that we haven't accounted for, and these variables could lead to unexpected changes in Apophis's trajectory. Moreover, the effect of space weather on our ability to track Apophis cannot be underestimated. In recent years, we've seen the dramatic effects that solar storms can have on our technological infrastructure. These storms can disrupt satellite communications, degrade radar systems, and interfere with the precise measurements we rely on to track asteroids. If a significant solar flare or coronal mass ejection coincides with the 2029 flyby, we could lose the ability to track Apophis with the level of precision we need. This is another source of uncertainty that could complicate our ability to assess the risks posed by the asteroid. But there's more at stake than just tracking the asteroid itself. The technology we use to monitor Apophis and other near-Earth objects is incredibly vulnerable to disruptions. Our satellites, telescopes, and ground-based observatories all rely on a stable technological infrastructure. If that infrastructure is compromised, whether by a solar storm, an asteroid collision, or some other factor, the consequences could be catastrophic. Without reliable tracking and communication systems, our ability to respond to a potential threat would be severely hindered. This is why it's not enough to simply track Apophis and hope for the best. We must actively work to build a more resilient infrastructure that can withstand the challenges posed by space weather, technological failures, and the inherent uncertainties of asteroid dynamics. This is where international cooperation and advanced risk management strategies come into play. The more we understand about the potential threats we face, the better prepared we will be to respond when the unexpected occurs. The reality is that while we can't predict every possible outcome, we can take steps to mitigate the risks and ensure that we are ready for whatever may come. As we approach the flyby of Apophis, it's clear that planetary defense is no longer a theoretical exercise. It's a practical, ongoing process that requires constant vigilance, adaptability, and collaboration. The 2029 flyby will provide us with invaluable data that will help us refine our models and predictions, but it will also raise new questions that will require further investigation. We must be ready to face these questions head-on and continue to adapt our strategies as new information becomes available. This is the essence of planetary defense, not just reacting to immediate threats, but actively preparing for the long-term future. The data we collect from the 2029 flyby will shape our understanding of Apophis, but it will also shape our approach to asteroid monitoring and risk management for decades to come. As we look ahead, it's not just about surviving one close encounter. It's about building a robust framework for planetary defense that can protect us from future threats, whether they come from Apophis, another asteroid, or something entirely unforeseen. One of the more troubling aspects of asteroid monitoring is the difficulty in predicting the behavior of a large, distant object like Apophis. Our models are based on a combination of observational data, mathematical formulas, and physical assumptions. Yet, as the 2029 flyby looms closer, the accuracy of these models is called into question. The variables that influence the trajectory and dynamics of an asteroid, such as its mass, rotation, surface characteristics, and interaction with Earth's gravity, can sometimes shift unexpectedly, as we've seen with other asteroids in the past. For instance, the way an asteroid spins, whether it rotates steadily around one axis or tumbles erratically, affects its thermal emission patterns, which in turn impact its Yarkovsky effect. This subtle force, which results from the asteroid radiating heat into space, gradually alters its orbit. A tumbling asteroid would have a more complex pattern of heat emission compared to one that rotates uniformly. But even with sophisticated models and advanced technology, determining whether Apophis is tumbling or spinning predictably remains an open question. If it does change its spin in response to the tidal forces during the flyby, the resulting changes in its orbit could dramatically alter the risk assessment. The uncertainty regarding Apophis's surface composition also adds another layer of complexity. While current models assume that the asteroid's surface reflects light in a particular way, we've seen time and again that surface properties can be more variable than expected. Apophis may be composed of a material with properties we haven't yet fully measured. A change in the asteroid's surface could trigger a chain of events that shifts its path and introduces risks that we currently cannot predict. We cannot overstate the importance of data collection during the flyby. Observing how Apophis interacts with Earth's gravity, especially in terms of any potential structural changes to its surface, will be crucial. By studying how the asteroid responds to tidal forces, researchers will be able to refine their understanding of how small changes in an asteroid's physical state can compound over time, potentially altering its long-term trajectory. These observations may reveal unexpected characteristics. Perhaps the asteroid's surface is more volatile, or its mass distribution is uneven. Whatever the findings, they will fundamentally change the way we assess asteroid risks. But as we prepare for the 2029 flyby, it is equally important to address the larger question of how we will respond if our predictions are proven wrong. If Apophis experiences significant changes that alter its orbit in unexpected ways, what will our next steps be? Planetary defense isn't just about monitoring and tracking. It's about being able to react quickly and decisively when new data challenges existing models.
The systems in place to monitor Apophis's path need to be agile enough to incorporate new findings and adjust our strategies accordingly. This is where the importance of international cooperation becomes apparent. The complexity of planetary defense requires the collective expertise and resources of multiple countries and space agencies. The potential threat posed by an asteroid like Apophis is global in nature, and the response needs to be coordinated across borders. Whether it's through better data sharing, joint mission efforts, or developing global risk management strategies, we must be prepared to collaborate and take swift action when necessary. But even with the best data and international collaboration, there will always be a level of uncertainty in planetary defense. Some risks will remain difficult to quantify, no matter how much technology and research progress. This uncertainty is not a reason to dismiss the danger, but a reminder that we must remain vigilant and flexible. The flyby of Apophis will give us valuable insight into the asteroid's behavior, but it will also open the door to a broader set of questions that will require further research and ongoing monitoring. What happens after 2029 is just as important as the flyby itself.
If Apophysis' orbit shifts in unexpected ways, we may be faced with a long-term challenge that will require constant recalibration of our models. This is why it is essential to continue studying Apophis after the flyby, using the data gathered to refine our understanding of the asteroid and its potential risks. The more we learn, the better equipped we will be to face future threats, whether they come from Apophis or other asteroids that may not yet be on our radar. In the coming years, we will learn more than we ever have before about Apophis. The flyby will provide the first real opportunity to observe its response to tidal forces up close, and the data gathered will be critical for refining the models we use to track and predict asteroid behavior. But the most important thing we can do is to keep our eyes open and our minds flexible. The 2029 flyby may be the most significant asteroid event of our lifetime, but it's just the beginning of an ongoing process of discovery, adaptation, and preparation. As we continue to learn from the flyby of Apophis, the need for continuous adaptation in planetary defense becomes clearer. It's important to remember that the flyby of 2029 is not a singular event, but rather a moment that will shape the trajectory of planetary defense for many years to come. The data we gather will be invaluable, but it will also highlight the need for further refinement in our models. The flyby is a test of not only our technology, but our ability to process new information, adjust to unexpected changes, and respond quickly if the situation shifts. One of the most crucial aspects of planetary defense is the concept of resilience, being prepared for the unexpected.
The tools we have at our disposal to monitor near-Earth objects, such as advanced telescopes, radar systems, and spacecraft, are powerful, but they're not infallible. These instruments provide a clear picture of the asteroid's position and trajectory based on current data, but there are always uncertainties, especially when considering the asteroid's long-term behavior. The flyby of Apophis offers an opportunity to test the limits of these instruments and refine the ways we track asteroids in the future. In the aftermath of the flyby, we'll have a clearer understanding of how tidal forces and the Yarkovsky effect, tiny but significant forces acting on the asteroid due to its rotation and thermal emissions, affect Apophis. These observations will be crucial for future asteroid encounters. We can only predict so much based on models, but these real-world tests will give us the hard data needed to update and fine-tune our risk assessments. For example, the rotation rate of Apophis may shift slightly, or its surface may experience subtle changes during the flyby, altering how it interacts with sunlight. These seemingly minor changes could have long-lasting effects on the asteroid's orbit. However, while these observations are critical, they are only part of the equation. We must also consider how planetary defense will evolve in the future to address asteroid threats. The 2029 flyby of Apophis is a key moment, but it's just one of many potential asteroid encounters we will face in the coming decades. As our understanding of asteroid dynamics improves, we will need to be prepared for more frequent close passes from other objects in the solar system. As we saw with Apophis, even small uncertainties can have a big impact on long-term risk assessments, so we must remain vigilant and ready to adjust our strategies. Another important aspect of planetary defense is the ongoing collaboration between space agencies around the world. No single country or agency can address asteroid threats alone. The challenges posed by near-Earth objects are global, and they require a unified, coordinated response. The 2029 flyby of Apophis will not only provide valuable data for NASA, ESA, and other agencies, but it will also help inform international collaboration in future asteroid defense efforts. Whether it's through joint mission planning, data sharing, or coordinating efforts to respond to a potential asteroid impact, the importance of global cooperation cannot be overstated. Furthermore,
The scientific community must continue to educate the public about the ongoing research and developments in planetary defense. While space agencies are working hard to ensure that we are prepared for the flyby and potential future threats, the general public often remains unaware of the complexities and uncertainties involved in tracking asteroids.
Clear communication about the risks, the research being done, and the plans for responding to asteroid threats is essential for fostering public understanding and support. If we want to continue advancing in planetary defense, the public must be aware of the challenges and the progress being made to protect the planet. Ultimately, the 2029 flyby of Apophis will serve as a critical reminder of how much we still have to learn about the objects that share our solar system. As we monitor and study Apophis in the coming years, the data we gather will shape the future of planetary defense. But the real work begins after the flyby, as we use the new information to adjust our models, refine our risk assessments, and prepare for future asteroid encounters. The 2029 flyby is not the end of the story. It's just the beginning of a long, ongoing effort to protect our planet from the unpredictable forces of space. As we move forward, we must continue to focus on the big picture. Planetary defense is not just about a single asteroid or a single close encounter. It's about preparing for a future where we are constantly monitoring the skies, studying near-Earth objects, and refining our understanding of the forces that shape our solar system. The tools, technology, and collaborations we develop today will play a critical role in safeguarding the planet for generations to come. The 2029 flyby is a turning point, but it's only one part of the much larger mission to protect Earth from asteroid impacts. Whether Apophis poses a threat or not, the lessons we learn from this flyby will help us build a more resilient, adaptable planetary defense system for the future. It's about understanding the unknowns, addressing the uncertainties, and making sure we are ready for anything that comes our way. As we continue to prepare for the 2029 flyby, the lessons learned from Apophis will undoubtedly influence not only how we handle this particular event, but also shape the future of planetary defense. One of the most critical insights from this event will be the ability to adjust and evolve as we gain new data. This is the true essence of planetary defense, an ongoing, dynamic process that doesn't end with a single flyby or asteroid encounter, but continues to grow as we gather more information, refine our models, and improve our technologies. The flyby of Apophis serves as a reminder that space is not a static environment. Asteroids and other near-Earth objects are constantly moving, and their trajectories can be altered by forces both predictable and unpredictable. Our understanding of these forces, while robust, is still incomplete. Every new asteroid encounter, like the 2029 flyby, provides an opportunity to learn more about how these objects behave and how they interact with the gravitational forces of Earth and other celestial bodies. This knowledge is crucial, not just for Apophis, but for all future asteroid monitoring and defense efforts.
One of the areas where continued research will be essential is in understanding the long-term behavior of asteroids. While our models may predict the position of an asteroid years or even decades into the future, there are many small variables that can throw off these predictions. Small changes in an asteroid's orbit, rotation, or surface composition can accumulate over time, shifting its path in ways that are difficult to predict. This is why ongoing observation after the 2029 flyby is so important. The data gathered during the flyby will provide us with a snapshot of Apophis's current state, but the true challenge will be to track how the asteroid's trajectory evolves in the years that follow. This is where international collaboration comes into play. No single agency or country can monitor every asteroid or near-Earth object, especially as we move forward and encounter more of these objects. The 2029 flyby will provide a valuable opportunity to see how we can work together to study and monitor a significant asteroid threat.
By pooling resources, sharing data, and coordinating efforts, space agencies around the world can ensure that we are prepared for whatever comes next. As the risk of asteroid impacts becomes more apparent, the need for a coordinated global response will only grow. It's also essential to recognize that the work of planetary defense is not just about tracking asteroids, it's about preparing for a wide range of potential outcomes. While the most likely scenario may be that Apophis will pass by without incident, we must remain ready for any unexpected changes. Whether it's a shift in the asteroid's trajectory, a disruption in our ability to monitor it, or a potential fragmentation event, we must be prepared for all possibilities. This means investing in technologies that allow us to better understand the physical properties of asteroids, including their composition, structure, and rotation. It also means developing contingency plans for deflection or mitigation if we find that an asteroid's path has become more dangerous than previously thought. The importance of understanding asteroid dynamics and planetary defense cannot be overstated. As we look to the future, we must continue to focus on improving our capabilities, expanding our knowledge, and remaining vigilant against potential threats. The flyby of Apophis will be an important event, but it is just one piece of a much larger puzzle. Each asteroid we track, each flyby we observe, brings us closer to developing a more complete understanding of how to protect Earth from these cosmic hazards. In the end, the lessons from Apophis's 2029 flyby will not just shape the future of planetary defense, but will influence the way we approach space exploration as a whole. By understanding the forces that govern asteroids and learning how to track and predict their movements, we will be better equipped to explore other parts of our solar system and beyond.
The data collected from this flyby will not only improve our models for asteroid deflection, but it will also contribute to our broader understanding of the dynamics of the solar system. We may not have all the answers right now, but the work we do in the coming years will lay the foundation for future generations to better understand and mitigate the risks posed by near-Earth objects. The flyby of Apophis is a reminder that space exploration and planetary defense are not just about preparing for a single event. They are about building a framework for understanding and responding to the unpredictable forces of space. And as we continue to refine our models and improve our technology, we move one step closer to ensuring that Earth is prepared for any cosmic challenge that lies ahead. As we move closer to the 2029 flyby of Apophis, it is increasingly clear that this will be more than just a celestial event for astronomers. It will mark a pivotal moment in the way humanity perceives the risks posed by near-Earth objects. While much of the public's attention is captured by sensational headlines and the immediate spectacle of a passing asteroid, the true significance of the flyby will only unfold in the years that follow. The close approach of Apophis, though seemingly benign, holds the potential to reveal critical insights into our understanding of asteroid dynamics and planetary defense. One of the key elements in our understanding of asteroid behavior is the degree to which small forces can accumulate and cause significant changes over time. The 2029 flyby of Apophis will serve as an unprecedented opportunity to test how tidal forces, the gravitational pull from Earth, can influence an asteroid's trajectory, surface composition, and even its internal structure. These tidal forces will stretch the asteroid, causing it to experience forces it has never felt before. What seems like a small disturbance may set off a chain reaction of events that dramatically alter Apophis's orbit and increase the risk in the future. Even though current models suggest that the asteroid will pass safely, these models are built on assumptions that could turn out to be wrong. The 2029 flyby is not just about tracking an asteroid in real time. It's about examining the very forces that govern the dynamics of space objects. The data we collect will help refine our models, giving us a clearer picture of the behavior of near-Earth objects as they approach our planet. In particular, tidal forces are often underestimated in their potential to cause significant changes to an asteroid's orbit. While it is common knowledge that Earth's gravity can nudge asteroids, The degree to which this can influence the asteroid's path over long periods of time is still uncertain. Even the slightest gravitational interaction can alter an asteroid's course, and over decades or centuries, this change could become amplified.
It's not simply about predicting the asteroid's path. It's about understanding how those small adjustments can accumulate and create unforeseen risks. Moreover, the precise nature of Apophis's surface composition is another factor that will be critical in understanding how the asteroid will behave during the flyby. While some asteroid compositions are well understood, we still know very little about the surface material of Apophis. Is it a dense, solid rock, or is it more of a rubble pile, a loose collection of rocks and dust bound together by gravity? This seemingly small detail could have profound implications for how Apophis responds to tidal forces. If the asteroid's surface is composed of loosely bound material, tidal forces could cause landslides, shifting surface material and altering its trajectory. These shifts, although subtle at first, could lead to much larger changes in the asteroid's path, impacting our ability to predict its future position accurately. This raises the important question: what happens when the asteroid's behavior changes in ways we haven't fully anticipated? If Apophis does indeed experience a shift in its surface material during the flyby, it could lead to long-term changes in its orbit that were previously unforeseen. The risk here lies in the fact that our models, though advanced, are still based on assumptions that may not hold true after the flyby. As we have learned from past encounters with other asteroids, the reality of what happens during a close pass can often surprise us. What we think we know about Apophis today could become obsolete once we have the full data set after the 2029 flyby. The subtle forces at play in space, such as the effect of the Yarkovsky effect, the asteroid's rotation, and its material composition, can all influence its trajectory in ways that are difficult to predict with certainty. This is why planetary defense is not a static field, but rather one that requires constant innovation and adaptation. As we study Apophis, we are not just looking for ways to track its trajectory more accurately. We are looking for new tools, new methods, and new ways of thinking about the forces that govern the motion of space objects. Every new asteroid flyby, every new observation brings us closer to understanding the complexities of these objects and how they interact with Earth's gravitational field. And it's not just about monitoring the asteroid during its flyby, it's about understanding how its behavior changes after the encounter and how we can adapt our models accordingly. For example, scientists will be paying close attention to the Yarkovsky effect during the flyby of Apophis. This phenomenon occurs when an asteroid absorbs sunlight and then re-emits it as infrared radiation. As the asteroid rotates, the re-emitted radiation causes a tiny yet continuous push that can alter its orbit over time. The force produced by the Yarkovsky effect is incredibly small, but over long periods, it can shift an asteroid's path significantly. However, the magnitude of the Yarkovsky effect on Apophis is still unknown. It depends on the asteroid's thermal properties, which are difficult to measure precisely. If the flyby introduces changes to Apophis's surface, such as a shift in its material composition or a change in its surface roughness, it could alter the Yarkovsky effect and cause unexpected changes in the asteroid's orbit. As researchers refine their models to account for these possibilities, they will also be studying how the 2029 flyby could push Apophis into a new trajectory, potentially making future encounters with Earth more frequent. If the gravitational forces during the flyby push the asteroid into a resonance with Earth, it could cause a chain reaction of close passes in the coming decades. This would increase the probability of a future collision or close call, making it all the more critical to continue studying Apophis long after the flyby.
This long-term perspective is vital because planetary defense is not just about reacting to a single event. It's about understanding the bigger picture and how to mitigate risks over time. The question of how to respond to changing asteroid dynamics is at the heart of planetary defense strategy. Current efforts to track near-Earth objects rely heavily on mathematical models and observations that give us a snapshot of where an asteroid is at any given moment. However, these models depend on the assumption that an asteroid's trajectory will remain relatively stable over time. When those assumptions turn out to be incorrect, or when new data reveals unexpected changes, we must be prepared to adjust our approach. That means developing not only more accurate monitoring systems, but also response strategies that can adapt to new information as it comes in. This is why it is so crucial to maintain a robust, adaptive framework for planetary defense. The flyby of Apophis in 2029 will provide us with valuable data that will help refine our models and improve our predictions. But it will also raise new questions and uncertainties that we must address. In planetary defense, the unexpected is always a possibility. It's not just about tracking asteroids, but about learning from them, understanding the forces at play, and being prepared for whatever changes those forces may bring. As we continue our efforts to monitor and understand the behavior of Apophis, it's important to consider not only the immediate risks posed by the asteroid, but also the broader implications of planetary defense. The 2029 flyby is an opportunity to evaluate our existing monitoring systems and our ability to adapt to unforeseen changes in an asteroid's behavior. While current models suggest that the risk of a collision with Earth is minimal, the key to planetary defense is the ability to respond swiftly and effectively to unexpected developments.
The ability to adapt to new data, reassess risk, and act when necessary will define the future of planetary defense efforts. The flyby of Apophis will also highlight the role of international collaboration in asteroid monitoring and risk mitigation. No single country can handle the threat of near-Earth objects alone. The complexities of tracking asteroids, predicting their future trajectories, and developing potential mitigation strategies require global cooperation. In the coming years, the increasing recognition of the importance of planetary defense will likely lead to more joint efforts between space agencies, governments, and private entities. This collaboration will be essential not just for Apophis, but for other near-Earth objects that may pose a risk in the future. As new data comes in after the 2029 flyby, we will be able to update and refine our models, improving our ability to predict the asteroid's path. However, there are always inherent uncertainties in these models. Asteroids, by nature, are unpredictable and often behave in ways that defy even the most advanced predictions. It's important to remember that the flyby of Apophis is not the end of the story. It's just the beginning of an ongoing process of discovery and adaptation. The data we gather will be critical in shaping future planetary defense strategies, but it will also open up new questions that we need to explore. One of the key lessons learned from studying Apophis and other asteroids is the need for resilience in planetary defense. It's not enough to rely solely on technology or models to keep us safe. We need to develop a system that can respond to changing conditions, react to new information, and adapt to unexpected events. The flyby of Apophis will serve as a reminder that our ability to defend Earth from asteroid impacts is not guaranteed. It requires constant vigilance, adaptability, and international cooperation. To truly protect our planet, we must be prepared for scenarios that go beyond just monitoring and tracking. Planetary defense efforts must also involve planning for potential mitigation strategies. If an asteroid like Apophis were to shift its orbit in an unexpected way, leading to a future risk of collision, what would our response be? Would we have the capability to divert the asteroid, or would we have to rely on other means to protect the planet? The continued development of asteroid deflection technologies is critical for ensuring that we are ready for these scenarios. Whether through kinetic impactors, nuclear deflection, or other methods,
we need to be able to respond quickly and effectively. In addition to mitigation strategies, public awareness and education are also crucial components of planetary defense. While the scientific community is at hard work developing strategies to track, monitor, and mitigate asteroid risks, the general public often remains unaware of the complexities involved in planetary defense.
As we approach the 2029 flyby, it is important to engage with the public and ensure they understand the potential risks posed by near-Earth objects and the steps being taken to address them. Clear communication about the ongoing research and the advancements in planetary defense will help build trust and support for these efforts. We must also recognize that planetary defense is not a one-time initiative. It's an ongoing, evolving process. The threat of asteroid impacts is a long-term concern, and it requires sustained investment in research, technology, and international cooperation. As we gather more data from the 2029 flyby and future asteroid encounters, we will gain new insights that will shape our approach to planetary defense. The ultimate goal is not just to survive one flyby, but to develop a robust system that can protect the Earth from future asteroid threats. Moreover, the lessons we learn from Apophis will have far-reaching implications beyond planetary defense. The technologies and methods developed to track and monitor asteroids will be useful in other areas of space exploration and science. For example, understanding how asteroids interact with solar radiation and how their orbits change over time will provide valuable insights into the broader dynamics of the solar system. As we continue to study Apophis and other near-Earth objects, we will improve our understanding of the forces that govern the movement of objects in space, ultimately enhancing our ability to explore other parts of the solar system. In conclusion, the 2029 flyby of Apophis is more than just an event. It is a critical moment in the evolution of planetary defense. It will provide valuable data that will help refine our models, improve our understanding of asteroid dynamics, and guide our efforts to protect Earth from future threats. But the flyby is also a reminder that planetary defense is not a one-time event. It's an ongoing process of learning, adapting, and preparing for the unknown. As we move forward, we must continue to refine our models, develop new technologies, and collaborate internationally to ensure that we are prepared for whatever challenges the future may bring. By building a resilient, adaptable planetary defense system, we can ensure Earth remains safe from the unpredictable forces of space. The flyby of Apophis is just the beginning of this journey, and the lessons we learn from this event will shape the future of planetary defense for generations to come. Let us embrace the challenges ahead, stay vigilant, and continue working together to safeguard our planet from the risks posed by near-Earth objects. As we look to the future, the 2029 flyby of Apophis will serve as a critical case study for planetary defense strategies. It will allow us to test the limits of our current technologies, refine our methods of tracking and predicting asteroid trajectories, and, perhaps most importantly, evaluate our ability to respond to unexpected events.
The unpredictability of space, combined with the dynamic nature of asteroids, means that we cannot simply prepare for a single scenario. The flyby will highlight the need for continual monitoring, ongoing data collection, and an adaptive approach to planetary defense. We must also acknowledge that as the global population grows and our technological infrastructure becomes more reliant on space-based systems, the stakes of planetary defense increase exponentially. Earth's increasing dependence on satellites for communication, weather forecasting, GPS navigation, and countless other services means that even small changes to the orbits of asteroids or disruptions caused by their proximity could have far-reaching consequences. If Apophis's flyby causes any disruption to satellite infrastructure, the impact could be felt globally, with economic, military, and communications systems being severely affected. This makes the importance of refining planetary defense not just about preventing a catastrophic impact, but also about safeguarding our increasingly interconnected world from the ripple effects of asteroid encounters. The next steps in planetary defense
must not only focus on better asteroid detection systems, but also include strategies for mitigating the effects of a near miss or flyby. In the case of Apophis, the asteroid's proximity could pose a threat to satellites, and even if the asteroid itself does not collide with Earth, the gravitational forces could cause significant orbital adjustments. This could result in new risks that we have yet to fully understand. For example, the shifting paths of smaller debris could increase the likelihood of other objects colliding with satellites or spacecraft, leading to cascading effects across the space infrastructure. The flyby of Apophis also reinforces the importance of collaboration between spacefaring nations. Planetary defense is a shared responsibility, and no single country can shoulder the burden of monitoring every asteroid or mitigating the effects of a potential impact. The United States, Russia, China, the European Space Agency, and other key players in space exploration must continue to work together, sharing data, pooling resources, and ensuring that all countries are prepared for potential asteroid threats. The success of planetary defense efforts hinges not only on technological advancement, but on international cooperation. Looking beyond Apophis, it is also essential that we prioritize the discovery of other near-Earth objects that have yet to be detected. While Apophis is currently one of the most closely monitored asteroids, it is far from the only one that could pose a risk. In fact, astronomers estimate that we have only discovered a fraction of the asteroids that may pass close to Earth in the future.
As our capabilities to detect these objects improve, we will be able to identify potential threats long before they come near Earth, giving us valuable time to prepare for any eventuality. The 2029 flyby is an excellent reminder of the critical need to fund asteroid detection programs and to continue improving our ability to detect and track near-Earth objects. In addition to detection, planetary defense also requires the development of response mechanisms. The field of asteroid deflection, changing the trajectory of an asteroid to avoid an impact with Earth, is still in its infancy, and while many ideas have been proposed, none have yet been proven in real-world scenarios. Kinetic impactors, nuclear deflection, and gravitational tugs are all potential methods, but these technologies need rigorous testing before they can be relied upon in an actual emergency. As we gather more data from that Apophis's flyby, it is crucial that we not only focus on understanding how the asteroid behaves, but also work toward developing viable deflection strategies. One method that could be employed in the future involves using a spacecraft to collide with an asteroid at high speed. By impacting the asteroid, we would be able to transfer momentum to it, altering its orbit slightly. This technique could be effective if we have enough time to make the adjustment, but it is not without challenges. A spacecraft must be able to precisely target the asteroid, and even a small error in trajectory could lead to a failed mission. There's also the issue of timing. If the asteroid is too close, there may not be enough time to mount a successful deflection effort. Another possibility involves using nuclear explosions to alter an asteroid's course. The idea behind this method is to detonate a nuclear device near the asteroid, creating a shock wave that would push the asteroid off course. However, the use of nuclear devices raises significant ethical, political, and logistical concerns. It would require international coordination and consensus, as well as careful consideration of the potential environmental impact. Gravitational tugs, on the other hand, would involve attaching a spacecraft to an asteroid and using the spacecraft's gravity to gently alter the asteroid's path over time. This technique is far less invasive than a kinetic impactor or a nuclear deflection, but it also requires precise maneuvering and may take years or even decades to achieve the necessary change in trajectory. The potential advantages of gravitational tugs are their precision and the fact that they would not risk fragmenting the asteroid, which could lead to additional problems. While these deflection strategies remain theoretical, the 2029 flyby will provide valuable data to inform their development. By observing how Apophis behaves as it passes through Earth's gravitational field, scientists will gain insights into how an asteroid's trajectory can be affected by outside forces. This data will be crucial as we continue to refine our methods of deflection and build more reliable planetary defense systems. Finally, it's essential to acknowledge that planetary defense goes beyond simply preventing asteroid impacts. It's about creating a framework that can anticipate, monitor, and respond to potential threats from space. This means investing in better detection systems, improving our understanding of asteroid dynamics, developing deflection technologies, and fostering international collaboration. The flyby of Apophis is just the beginning of a long process to ensure the future safety of our planet, and it's a reminder that we must remain vigilant and adaptable in the face of the unknown. As we continue to refine and expand our planetary defense efforts, one of the crucial aspects to address is the integration of new technologies and methodologies. The space industry is advancing at an unprecedented rate, and these innovations can be leveraged to enhance our monitoring capabilities and improve our response times. The development of more advanced telescopes, better radar systems, and even space-based sensors will allow for early detection of potential asteroid threats. But equally important is the need for continuous technological upgrades and a commitment to exploring innovative ways to address new challenges. In the coming years, we will need to focus on advancing our asteroid tracking systems and increasing their accuracy. Current systems provide valuable data, but as more near-Earth objects are discovered, the volume of data generated will increase exponentially. This presents a unique challenge. How can we manage and analyze this vast amount of data efficiently? The answer lies in the integration of artificial intelligence, AI, and machine learning. These technologies can help us process and analyze data much faster, enabling us to identify patterns, predict trajectories, and pinpoint potential threats more effectively. By incorporating AI into our asteroid monitoring efforts, we can increase the speed and accuracy with which we assess the risks posed by these objects. AI can also play a pivotal role in planetary defense strategies, particularly when it comes to decision-making and response planning. In the event of a near-Earth object threatening Earth, quick decisions need to be made about whether to attempt deflection or evacuation. AI can help us analyze the situation in real time, considering the myriad of factors that will influence the outcome. It can help us choose the best course of action based on the data we have, providing decision-makers with more informed, actionable insights. In addition to AI, the continued development of space-based technologies will be vital. For example, space-based telescopes and radar systems will provide more accurate and real-time data about asteroids, allowing us to track their movements with greater precision.
These advancements in technology will give us a better understanding of the composition, rotation, and trajectory of near-Earth objects. However, while these tools are invaluable, they are only part of the equation. We must also improve our ability to respond to potential threats once they are detected. In order to effectively address asteroid impacts, we must develop and implement deflection technologies that can be deployed quickly and efficiently. Whether through kinetic impactors, nuclear deflection, or gravitational tugs, we need a range of viable options to choose from, depending on the size and composition of the asteroid. As we continue to study Apophis and similar objects, we must also ensure that we are constantly testing and refining these deflection strategies. Each new asteroid encounter, each new piece of data, provides an opportunity to learn and improve. One of the most promising avenues for asteroid deflection is the use of kinetic impactors. This method involves sending a spacecraft to collide with an asteroid at high speed in order to transfer momentum to the object, thus altering its trajectory. While the concept is straightforward, the execution is far more complex. The spacecraft must be able to precisely target the asteroid, and even the smallest error in trajectory could cause the mission to fail. Additionally, the timing of the impact is critical. The spacecraft must hit the asteroid with enough force to alter its course without fragmenting it. This is a delicate balance that requires careful planning and a deep understanding of the asteroid's physical properties. Nuclear deflection is another option that has been proposed.
This method would involve detonating a nuclear device near the asteroid to generate a shock wave that would push the asteroid off its course. While this method would be effective in theory, it presents a number of challenges. First, there are significant political and ethical concerns surrounding the use of nuclear weapons in space. Second, the effectiveness of a nuclear explosion in altering an asteroid's trajectory depends on the size of the object, its composition, and how it absorbs the shockwave. Like kinetic impactors, nuclear deflection would require precise targeting and timing, and the risk of failure could have catastrophic consequences. Gravitational tugs, though less dramatic, offer another potential method of deflection. This technique would involve using a spacecraft's gravitational pull to slowly alter the asteroid's orbit over time. While this method is less risky than nuclear or kinetic impactors, it also requires far more time and precision. It may take years or even decades to achieve the necessary shift in the asteroid's trajectory, making it less suitable for short-term threats, but ideal for smaller objects or those that we can track well in advance.
Regardless of which deflection method is chosen, the success of any planetary defense strategy hinges on our ability to detect and track asteroids far in advance. The earlier we can identify a potential threat, the more time we will have to develop a response and implement a deflection strategy. This underscores the importance of continued investment in asteroid detection technologies, as well as the need to improve our global tracking networks. Moreover, the 2029 flyby of Apophis is a reminder of the unpredictability of space. Even with the most advanced detection systems in place, we are still working with incomplete data. Asteroids are dynamic objects, subject to forces that we can't always predict. This is why it's crucial to remain flexible in our approach to planetary defense, continually reassessing our models and strategies in light of new information. The more we learn about asteroids like Apophis, the better equipped we will be to handle the challenges that lie ahead. While the 2029 flyby of Apophis will certainly be a momentous event, it is not the end of the journey. It is simply one chapter in the ongoing story of planetary defense. We must use this event as an opportunity to learn, adapt, and improve. The lessons we learn will shape the future of asteroid monitoring, deflection technologies, and our overall approach to protecting Earth from potential impacts. And as we move forward, we must continue to build on the foundation laid by this event, constantly refining our knowledge and capabilities in the face of new challenges. Planetary defense is not just about protecting Earth from a single asteroid. It's about ensuring the long-term survival of our planet and the future of humanity. The tools and technologies we develop today will shape the world of tomorrow, and it is our responsibility to ensure that we are prepared for whatever the cosmos may throw our way. The flyby of Apophis is a reminder of both the risks we face and the incredible potential we have to protect our planet. As we look ahead, let us stay vigilant, stay informed, and continue to work together to safeguard the future of Earth. As we press forward in our efforts to improve planetary defense, it's vital to understand that asteroid monitoring and deflection aren't the only components of this broader effort. A comprehensive planetary defense strategy must include public outreach and education, infrastructure resilience, and international collaboration. These efforts will ensure that not only the scientific community, but also the global public is prepared for any eventuality. One critical aspect of this is fostering public awareness about the reality of asteroid threats and the steps being taken to mitigate them. While many people are aware of the existence of asteroids, they may not fully understand the risks or the complexity of planetary defense.
Asteroids like Apophis, though far from Earth in the grand scheme of space, still present significant challenges for our technological and strategic preparedness. Education is the key to ensuring that when an asteroid is detected, the public is not caught off guard by what could be a rapidly evolving situation. By educating the public, we not only help build support for planetary defense efforts, but also promote a better understanding of the need for continued investment in asteroid detection and research.
The more informed the public is, the more likely it is that governments and space agencies around the world will continue to allocate the necessary resources to protect Earth. This public support is crucial because without it, long-term investments in asteroid detection and defense technologies may not be sustained. Public awareness campaigns, outreach programs, and educational initiatives must become an integral part of planetary defense to ensure that these efforts are not only scientifically effective, but also publicly supported. Moreover, protecting our space infrastructure and technological systems from the effects of asteroid flybys is a critical aspect of planetary defense. As we've seen with Apophis and other asteroid encounters, there is a risk that asteroid flybys could disturb the orbits of satellites, which are essential to our global communication networks. Given that we rely on satellites for everything from weather forecasting to global positioning systems, GPS, any disruption to their orbits could have catastrophic consequences. This makes it crucial not only to defend against a potential asteroid impact, but also to ensure that our infrastructure can withstand the gravitational forces that may arise from such close passes. This leads to the need for improved space weather forecasting and mitigation strategies. Just as Earth faces weather systems like hurricanes and solar storms, space is subject to its own types of weather, including gravitational disturbances from passing asteroids. These disturbances can have unpredictable effects on our satellites and other space-based infrastructure. By developing more resilient satellite systems, we can reduce the risk posed by gravitational interactions between asteroids and Earth's space environment. This would allow for better protection of both our communications infrastructure and any critical systems that rely on satellite technology. Furthermore, while asteroid monitoring and defense technologies are the cornerstone of planetary protection, there is another important dimension to consider: global cooperation. No single country or agency can independently handle the global risks posed by asteroids. The 2029 flyby of Apophis is a stark reminder that planetary defense is an international concern. As we move forward, the only way to ensure comprehensive protection for Earth is through the collaboration of space agencies and governments worldwide.
This could involve pooling resources for asteroid detection, sharing data between countries, and developing joint strategies for asteroid deflection. International collaboration is essential because space threats are global in nature. An asteroid impact does not recognize national borders. A collision with Earth, or even a close flyby that disrupts satellite orbits, could have global consequences. For instance, if an asteroid were to alter its trajectory during a flyby and come dangerously close to Earth years later, the resulting effects would be felt worldwide. In such cases, it is imperative that countries work together, share their resources, and take coordinated action. As we face the growing number of near-Earth objects, this cooperative approach will become increasingly important. The 2029 flyby of Apophis is an opportunity to not only test the effectiveness of our planetary defense systems, but also to strengthen the bonds between spacefaring nations. If the flyby causes any disruption to our infrastructure or leads to unexpected findings, the lessons learned will be invaluable in shaping future efforts to defend Earth. This global cooperation must extend beyond space agencies and involve scientists, engineers, politicians, and even the general public. A unified, coordinated response to asteroid threats will be critical for ensuring the survival of life on Earth in the face of potential cosmic hazards. In addition to strengthening international collaboration, we must also continue to invest in space exploration technologies that may one day be used to proactively prevent asteroid impacts. While current asteroid deflection strategies focus on reacting to potential threats, future advancements could allow us to take a more proactive approach. For instance, by sending missions to intercept and study near-Earth objects before they become a direct threat,
We could develop more targeted deflection strategies and prepare mitigation techniques well in advance of any potential danger. Developing the technology to not just monitor, but actively engage with asteroids before they become a threat will require investment in innovation. Future missions may involve sending spacecraft to rendezvous with asteroids, studying their composition, surface features, and internal structure in detail, and testing deflection techniques. The more we know about asteroids before they approach Earth, the better equipped we will be to prevent a catastrophic collision or close pass. Moreover, these missions could serve dual purposes: planetary defense and scientific exploration. Studying asteroids up close will not only help us better understand their behavior, but also provide valuable insights into the formation of the solar system. Many asteroids are considered to be leftovers from the formation of the solar system, preserving clues about the early days of the solar system.
By combining planetary defense efforts with scientific exploration, we can advance our understanding of both the risks posed by asteroids and the potential benefits of studying them. In conclusion, while the 2029 flyby of Apophis is a critical moment in the history of planetary defense, it is just one piece of a much larger puzzle. The flyby will provide valuable data and insights into how we monitor and respond to near-Earth objects, but it is only the beginning of an ongoing effort to protect Earth from future asteroid threats. By strengthening international cooperation, improving our detection and deflection capabilities, investing in new technologies, and educating the public, we can build a more resilient, adaptive planetary defense system that will safeguard Earth for generations to come. The 2029 flyby is a reminder that the risks posed by near-Earth objects are real and present. But it is also an opportunity, a chance to learn, to innovate, and to prepare for whatever the cosmos may throw our way. As we move forward, let us remain vigilant, adaptable, and united in our efforts to protect the planet we call home. As we prepare for the 2029 flyby and the challenges it will present, it's important to acknowledge that the issue of planetary defense goes far beyond just one asteroid or one event. While Apophis's flyby may serve as a defining moment, it is part of a much larger, ongoing effort to protect Earth from a host of potential space-based threats. The key to this broader defense strategy lies not just in how we respond to a specific asteroid, but in how we build systems, technologies, and policies that allow us to anticipate, monitor, and mitigate risks over the long term. Asteroids, while perhaps the most immediately noticeable threat, are not the only potential dangers that we face from space. Other objects, such as comets, debris from past space missions, and even rogue satellites, pose a risk to the stability of Earth's orbit and our technological infrastructure. As our reliance on space-based systems continues to grow, the importance of defending Earth's space environment becomes even clearer. We need to expand the scope of planetary defense to account for the various types of space threats that could disrupt our way of life. Moreover, while the focus on asteroid deflection technologies is vital, we must also consider mitigation strategies for the consequences of near-Earth objects or space debris colliding with Earth. Even if we can prevent an asteroid from impacting the planet directly, the long-term effects of an asteroid flyby, such as disruption to satellite orbits or damage to space infrastructure, can be devastating. Space debris, for example, is an increasing concern as more satellites are launched into orbit, creating a hazardous environment in space that could interfere with both scientific missions and commercial activities.
One emerging solution to this issue is the development of space traffic management systems, similar to air traffic control systems for aviation. As the number of objects in space increases, so does the need to track their movements with high precision. By developing more advanced systems to monitor and manage the movement of satellites, asteroids, and other objects in space, we can reduce the risk of collisions and ensure the safe use of space for exploration and communication. This will also make it easier to predict the movements of objects like Apophis and determine whether they will have any adverse effects on Earth's space-based infrastructure. As we continue to refine and expand our planetary defense strategies, it is important to recognize that we are not just reacting to current threats, we are preparing for the future. The data we gather from Apophis, combined with future asteroid flybys, will serve as a foundation for the development of more advanced defense technologies and more effective international cooperation. This proactive approach is essential because the risks we face from space-based threats are not static, they evolve over time. As our technology advances, so too will the capabilities of potential threats. To keep pace, we must continue to innovate, collaborate, and invest in new solutions. Planetary defense is not only about dealing with the consequences of an asteroid or space debris hitting Earth. It's about preventing those consequences from happening in the first place. This is why international space agencies, along with private sector players, are putting more emphasis on building reliable, sustainable space infrastructure that can withstand potential impacts. Space-based missions, such as those proposed for asteroid deflection, will not only focus on preventing impacts, but will also aim to increase our understanding of how these objects behave and interact with Earth's gravitational field. The ability to predict and alter the course of an asteroid in real time is an ambitious but achievable goal, and the 2029 flyby of Apophis is an important milestone in that journey. Equally important is the need for long-term funding and support for planetary defense initiatives. As we continue to monitor and track near-Earth objects, we must ensure that funding for asteroid detection, research, and mitigation technologies remains a priority. Governments and space agencies must commit to sustaining these efforts, and the private sector should be encouraged to invest in technologies that could contribute to asteroid defense. By working together, public and private entities can create a more resilient infrastructure for planetary defense, one that can respond not just to known threats, but also to emerging risks that we may not yet fully understand. In addition to technological advancements, another crucial element of planetary defense is fostering global partnerships and agreements on how to respond to asteroid threats.
The risks posed by near-Earth objects are not confined to any one country. They're global in nature. Just as countries collaborate on climate change, the spread of infectious diseases, and other global challenges, so too must we work together to safeguard the planet from asteroid impacts. This collaboration could involve sharing data, resources, and expertise, as well as developing joint mitigation strategies that ensure a coordinated response in the event of a potential impact. By building international partnerships, we can ensure that planetary defense is a collective priority with shared responsibility across borders. The 2029 flyby of Apophis is a crucial test of our ability to monitor, track, and respond to potential threats from space. However, it is only the beginning. As we gather more data, refine our models, and continue to invest in planetary defense technologies, we will be better prepared to face future challenges. The flyby will help us learn more about how asteroids behave and how we can track their movements more accurately. But more importantly, it will serve as a reminder that planetary defense is not just a scientific issue. It's a global, long-term challenge that requires the commitment and collaboration of nations, industries, and individuals alike. As we look ahead, we must remain vigilant and adaptable. The risks posed by near-Earth objects are real, but they are not insurmountable. With continued research, investment, and international cooperation,
we can ensure that Earth remains protected from the hazards of space. The flyby of Apophis may be the first major asteroid event that tests our planetary defense capabilities, but it will not be the last. The real work begins after the flyby, as we use the lessons learned to strengthen our strategies and continue to prepare for the future. Let us move forward with a sense of purpose and unity, knowing that the actions we take today will protect future generations from the risks posed by space. Whether it's refining our detection systems, developing new deflection technologies, or building stronger international partnerships, we have the tools, the knowledge, and the opportunity to make a difference. The 2029 flyby is an important moment in history, but the future of planetary defense will be shaped by the steps we take today. Looking even further into the future, it is important to recognize that planetary defense is not only about mitigating asteroid impacts, but also about understanding the long-term dynamics of the solar system. Asteroids like Apophis are just one part of the vast, ever-changing space environment that surrounds Earth. While the primary focus today is on near-Earth objects, the study of these objects provides valuable insight into the larger solar system and its history.
Many of the techniques and technologies we are developing for planetary defense have broader applications, from advancing space exploration to better understanding the forces that shape the cosmos. One of the key benefits of planetary defense research is the deepening of our understanding of the solar system's formation. Asteroids like Apophis are often referred to as fossils of the early solar system, remnants of the materials that coalesced to form the planets. By studying these objects in detail, we can gain a better understanding of the conditions that existed in the early solar system, as well as the processes that led to the formation of Earth and other planets. This research is not just about protecting our planet, it's about understanding where we come from and how the solar system has evolved. Moreover, planetary defense research is likely to have unforeseen benefits in other areas of science and technology. The technologies developed to track and monitor asteroids, such as advanced radar systems, telescopes, and space-based sensors, are directly applicable to other scientific fields. For instance, improving our ability to monitor asteroids will also enhance our capacity to monitor other space objects, such as comets, space debris, and even the space weather that affects our satellites and communications. The tools and systems we develop today will have wide-ranging applications in many other areas of space science, opening up new frontiers for exploration and discovery. In addition to technological advancements, planetary defense research will also push forward our understanding of human space exploration. By studying how asteroids interact with Earth and how they can be deflected, we are also learning more about the challenges of space travel and exploration. If humanity is to venture beyond Earth, whether to Mars, the Moon, or farther into the solar system, understanding how to safely navigate and interact with space objects will be essential. The technologies and knowledge gained through planetary defense efforts will play a critical role in the future of space exploration, helping ensure the safety of astronauts and spacecraft as we extend our reach beyond Earth's atmosphere. As we continue to focus on the immediate threat of near-Earth objects, it's important to consider how planetary defense fits into the larger vision of human space exploration. The goal is not just to protect Earth from potential asteroid impacts, but to ensure that we are prepared for the next steps in space exploration. This involves investing in the technologies, infrastructure, and international collaboration needed to protect not only our planet, but also the broader space environment.
In the future, planetary defense may evolve into a broader effort that includes protecting other planets and moons from the same risks we face on Earth.
The question of how to manage space threats, including asteroid impacts and other hazards, will only become more important as humanity ventures further into space. If we are to establish permanent human settlements on the Moon or Mars, we will need to ensure that these colonies are protected from the same space-based risks that we face on Earth. While planetary defense research today is primarily focused on protecting Earth, it lays the groundwork for protecting human outposts on other celestial bodies in the future. This means that the work we do today in tracking, monitoring, and deflecting asteroids is not just about safeguarding Earth, it's about preparing humanity for the challenges of space colonization and exploration. Looking forward, space-based industries and technologies will become increasingly important, and the risks we face from space objects will only grow as humanity's footprint in space expands. With the rapid development of private space companies and the growing interest in asteroid mining and space tourism, it's critical that we create the legal, technological, and regulatory frameworks needed to protect both Earth and the space environment we're entering. Just as we have developed laws to protect our planet from environmental degradation, we will need to develop policies to protect space and ensure that future generations can safely explore and utilize space without falling victim to the same risks we are working to mitigate today. As we continue to learn more from the 2019 flyby of Apophis and future asteroid encounters, we will uncover new insights into the risks we face from space. Every new discovery, whether it's related to asteroid composition, trajectory, or the impact of tidal forces, will help us refine our models and enhance our planetary defense strategies. But the real test will come when we are faced with an asteroid threat that we cannot predict or that our current technologies cannot address. This is why planetary defense must remain a priority, because the unknowns are as important as the knowns, and we must be ready for anything. The work of planetary defense, therefore, is never done. We will never reach a point where we can say that we have eliminated all risks posed by asteroids or other space threats. Instead, the work will continue to evolve, with new challenges emerging as we gain a better understanding of the complexities of space. But as long as we continue to invest in research, collaboration, and innovation, we will be better prepared for whatever the future holds. Whether it's tracking Apophis or deflecting a future asteroid threat, we will be ready to face the unknown and protect Earth from the unpredictable forces of the universe.